Hello there, Mr. Sutton here, bringing you this AP Calculus 4-1 Part 2 homework solutions on extreme values. In this one, we're focusing on calculator-based problems involving finding absolute mins and maxes and also the extreme value theorem.
For this no calculator problem, we want the absolute max value for this polynomial on the interval from -2 to 4. So to get that, we're going to have to test out the endpoints as well as critical values in the original function. Let's get those critical values now. We'll do that by taking the derivative, which is 3x squared minus 6x, and then that 12 is just a 0, so we don't have to write it. So now there's no places where this is going to be undefined. We just have to figure out where it takes on a value of 0. So I can do that by factoring out a 3x. That leaves me with an x minus 2 inside. And that means my x values that come out of this are 0 and positive 2. Now, taking a look at our interval, 0 and positive 2 are both between -2 and 4, so we have to test these out along with the endpoints of -2 and 4. So let's run our candidates test. We'll start with -2. We'll just go from most negative to most positive so we don't miss anything. So this is the f of -2 that we're trying to find right now. That's going to be, let's see here, we've got -8. This is minus 12, so -20, plus 12 is going to be -8 again. Now we're going to plug in 0, which is a little bit easier. That zeroes out all these things with x's, leaving us with just 12. So far, x equals 0 is the winner out of these. But let's try out the other ones here. So we also needed to try positive 2. That's going to be 8 minus 12 plus 12, so that's going to be positive 8. And then finally 4, plugging that in, we've got 64 minus, let's see, this is 3 times 16, so minus 48. That's 16 plus 12 is 28. Well, it looks like 4 is now the winner, so choice A, max value at 4. For this problem, we're given the function f of x equals absolute value of x. We want to know which of these statements are true. Now, this was, interestingly enough, a calculator question, so if you wanted to, you could go to your calculator and actually graph this out. So here I am in my y equals. I mean, why not if they're going to let me do it? Alpha window gives me a little submenu, and abs is what we're looking for. That's the absolute value. Absolute value of x. I don't know what window to use. Let me just do zoom 6, standard window. There it is. I mean, we already knew what this looked like if you paid attention in pre-calculus earlier, but there it is again. So, statement 1, f is continuous at x equals 0. Well, we have a corner going on there, but that doesn't break continuity itself. We're definitely continuous there. We're continuous everywhere, actually, on the absolute value function. There's no gaps or breaks or anything. So choice 1 is confirmed. This is a yes. On to choice 2, differentiable at x equals 0. That's a corner right there. We know corners are one of those differentiable spots because there's an abrupt change in slope. So because of our corner, that's going to be a no. It's not differentiable there. So anything with 2 in it's got to go. So choices E and B can be eliminated. And anything that doesn't have 1 can go. So C is also out of the running. So it's really down to whether or not statement 3 is true. F has an absolute min at x equals 0. If you know a little bit about the absolute value function, you know it's basically 2 lines sandwiched together piecewise style. So we have this line for outputs. For whenever you have negative inputs, it gives you positive outputs, and the more negative the input, the more positive the output. So it's a line. It's another line in the other direction as well. So this corner down here, the bottom of the V, that is as low as we get at x equals 0 in this case. So because of that whole bottom of the V reasoning, that's a yes. That is the absolute min for this function. So then choice D for options 1 and 3. For this problem, we have this crazy-looking polynomial, and we have the interval from 0 to 9. We want the absolute max for this function over that interval. Or we want to know what the x value is, at least that gives us the absolute max. So we're going to have to test out the endpoints for 0 and 9. We're going to have to plug both of those in here. 0 is not so bad. 9 is going to be kind of annoying, but we'll cross that bridge when we get there. Let's get our other candidates, which are going to be whatever critical values this function has on the interval from 0 to 9. So to find those, let's take the first derivative. So let's see here. Using our power rule, we've got 3 times a third, which cancels. That's just going to be plain old x squared for that first term. Next one, we have 8x followed by 12. 5 is just 0, so we don't have to write it. So this is our derivative. We want to see where this equals 0. We're also interested in where the derivative in general does not exist for critical values, but this one exists everywhere, so it's just the zeroing values we need. I can factor this. Two things that multiply to 12 and add up to negative 8 would be x minus 2 and x minus 6. So that means x equals positive 2 and positive 6 will also be candidates. These are all our candidates. The 2, the 6, 0, 9, 4 is not a candidate. So we can eliminate choice C right off the bat. It's not on our list of numbers to try. All right, but 0 is. Let's try that one first. We're going to have to try all of them because you never really know until you've seen all the candidates. They all have to speak their piece on this one. So we need f of 0. That zeroes out everything that has an x, leaving us with only negative 5. So that's kind of the winner by default so far. Next, let's try out f of 2. That's the next number. So that's going to be kind of nasty with this fraction here. But we've got essentially 8 over 3 minus, let's see, this is 4 times 4, so minus 16 plus 24 minus 5. To make my life a little bit easier, I'm going to combine all these non-fractions first. So this is going to be, let's see, negative 16 and 24 is 8, minus 5 is a 3. So this is 8 thirds plus 3. So 8 thirds plus 9 thirds, which is 17 thirds, which is, well, it's a positive number, so it's already winning because our only other option is a negative number. Let's move on and see if we have something that looks bigger than this. We have to also test out now 6. Testing 6 out, we've got, let's see here, 6 to the third is 216, but we have to divide that by 3. Well, I can just take one of those 3 6s and multiply it by 1/3. So that would be a 2 times 6, which is 72. Well, that was fun. And now we have to plug 6 into the next thing. So this is 36 times 4. That's going to be, let's see here, 4 times 30 is 120. 4 times 6 is 24. So minus 144. If we do a little clever arithmetic, I guess we could multiply it by hand, but whatever. And then we have 6 times 12, which is 72, minus the 5 over there. So as nasty as this was to get these individual things, 72 and 72 is 144. That cancels out the negative 144. So we're just actually left with negative 5 at the end of that one. Loser, not beating out the positive number here. All right, now we have 9. So that's going to be also fun to multiply. We have 1/3 of the first of these 3 9s is going to be 3. So we have 3 times 9 times 9. That's 3 times 81. That's going to be 243. Next, we have 4 times 81, which is going to be 3, let's see here, 4 times, that would be 324, yep. And then we have 9 times 12, which is 108, then minus 5. So this is more painful to get together here, but let's give it a shot. So let me see here. We've got 108. I'll do the positive numbers first. So I have 108 and 243 being added together. That's going to be 351. 351, take away 324. That's going to be 27 minus another 5 is 22. There we go. So at the end of the day, we were looking for the biggest value. That happens right here. 22 is definitely way bigger than 17 over 3. 22 would have been like 66 over 3. So our max happens at x equals 9, choice E.
For this problem, the first derivative of a function is given by this cosine squared of x over x minus 1/5 function. They just want to know how many critical values f has on the interval from 0 to 10. So critical values are going to be places where the first derivative is either 0 or undefined. Now, just kind of looking at the structure of this thing, the only place this is going to be undefined is at x equals 0 because we'd be dividing by 0, but they're not including 0 on the interval. It's excluded because this is the open interval from 0 to 100. So we don't have to worry about the undefined stuff. At that point then, we're just worrying about where does f prime actually equal 0. And we are going to be able to use the calculator on this one. So let's fire up Desmos and see how many times this crosses the x-axis. So here I am in Desmos, and let me do my function. So I'm going to do fraction, and then to do cosine squared of x, I need to do parentheses cosine of x and then square that. That's what that really means. And that's all over x. And we have minus 1/5. So this is our derivative function. They wanted that between 0 and 10. So let me just go to my wrench here and change my interval a little bit. Let me make the x-axis go from, say, -1 to 11. I'll just go a little further than I need to. And let's look at the graph. Now, there's a few places we're definitely crossing, but it's kind of hard to tell. And you can click on the function and then click on the little gray dots where it's crossing and see the exact places. But it's actually just a little easier just to go back into my settings and let me just adjust my y-axis so that I'm going from maybe like negative, I don't know, 0.6 to positive 1.6. Just zoom in a little bit here. And if I zoom in just a little bit vertically, I see that there's exactly 1, 2, 3 places where we're crossing. So here's a version of the graph that I just did there, and we're seeing 3 crossings. So this means that we have 3 critical values for the graph of f. Choice B.
For this problem, we have a function f that's defined for all x on a closed interval from a to b. If f somehow does not attain a maximum value on that closed interval, which of the following of these must be true? So we're just going to go through and eliminate what we can. Option A, f is not continuous on a to b. So we have a function that's defined, we have a closed interval, and yet there's no max. The extreme value theorem says that we're going to have a max if we have a closed and continuous function. We already have the closed part of it. If we don't have a max, the only way we get out of having a max is if we broke the continuity piece of this. So we can't be continuous if we have a closed interval with no max. There's no way this function is also continuous because that would break the EVT. So this is a true statement right here. F is not continuous. And there's a few ways f could be not continuous. One way would be we might have a vertical asymptote on there. Another way, just to draw an alternate graph for this, and you'll see why I'm doing this in a sec, is we might have one of these situations. We might have this kind of discontinuity. And then we'd have a function that is certainly defined for all values, but doesn't have a max, because the max would have been this spot here that has the open dot. Since you have an open dot here, you're getting closer and closer, but never quite getting there, so you can always get a little bit closer to what should have been your maximum value. So with this picture in mind, we're going to take a look at some of the other answer choices. Like choice B, they're saying f is not bounded on a to b. So basically saying that the y values either decrease or increase without bound. But this is implying that you have to have some kind of asymptote in order for all these conditions to be met. And we see down here that you don't need an asymptote. You just need a hole, and then you can end up not having a max even though all these other conditions are met. So choice B is a no. A hole is good enough for meeting all these conditions. Choice C, f does not attain a minimum value on a to b. Well, it may or it may not. I mean, here's a situation that meets all the conditions, and yet here's a minimum value. The min and the max are independent of each other, so this is also false. Choice D, graph has a vertical asymptote. We pretty much dealt with that in choice B. And then E, the equation f prime of 0, or f prime of x equals 0 does not have a solution. They're saying there's no smooth turnarounds, but there certainly could be. We also could have a plateau, in which case you would not have a maximum value. So lots of ways for this last one to be disproven. So that's also a no. You could have a min, you could have a local max. So lots of ways to have f prime of x equaling 0, even though you don't have an absolute max. So this is a no when all is said and done, meaning that answer choice A, the first one we saw that was actually true, ends up being the one we're going to pick. For this problem, we're saying that g is a continuous function on a closed interval from 0 to 1. G of 0 is 1, g of 1 is 0. Which of the following is not necessarily true? So there's a whole bunch of things that we're going to be able to prove are true then. Only one of these is not provable. So choice A, there exists a number h from 0 to 1 such that g of h greater than or equal to g of x for all x in 0 to 1. So basically we're saying that there's a maximum. There's some number between 0 to 1 that when I plug it in, I get it as a y value bigger than or equal to all the other y values on this interval. Is that true or not? Well, they said that we had a continuous function on a closed interval. If we have a continuous closed sort of situation, that means that the extreme value theorem, the EVT, guarantees we have a max and a min, an absolute max and a min on that interval. So that is guaranteed. Choice A is necessarily true. Choice B, for all A and B, if A equals B, then G of A equals G of B. Basically saying the same input gives me the same output. And that's definitely true. The only way you could avoid that is if you had some kind of weird non-function sort of situation where plugging in the same value sometimes gave you a different number. But they said it was a function, so we're good on this one. All right, C. There exists a number between 0 and 1 such that g of h is 1/2. Well, the key on this one is these values they gave us in the beginning. They said that we have, basically we're going from the point 0, 1 to 1, 0. So 0, 1 is like 1 on the y-axis, and we're going to 1 on the x-axis. And we're guaranteed that we're going to pass through a y value of 1/2. The reason for that is that we have a continuous function, and 1/2 is between the starting and ending values of 0 and 1. So that means since we have a continuous function, we're guaranteed to hit everything in between 0 and 1 by the intermediate value theorem. This guarantees it. So this means that choice C then is a true statement. This has to happen because of the IVT. D is kind of like C, only now it's 3/2 instead of 1/2. Well, 3/2 is not between 0 and 1. So although we might hit the y value 3/2, we're not guaranteed to hit it. So because we're not in that interval, we can't guarantee it. This is not necessarily true, therefore it's false. But let's just check out choice E to be on the safe side. For all h, a limit and function value at h are the same thing. Well, since we have a continuous function, we're guaranteed the limit and the function value always match up. So this is also a true statement. So then D is the only one we can't prove, and that's our answer choice. For this problem, we have a function that's defined on a closed interval from 0 to 1 and satisfies, let's see, f of 0 equals f of 1/2 equals f of 1. Okay, that's fine. On the open interval from 0 to 1, f is continuous and, well, this is interesting, strictly increasing. Which statement is true? And we have a whole bunch of statements about mins and maxes on the closed interval. So if we were to rate this on like the Pepper scale rating, whatever that's called, this would be somewhere between habanero and ghost chili level. This one is very tricky because on the one hand, this function is defined everywhere between 0 and 1, including 0 and 1. And we know that the y values at the beginning, the middle, and the end of the function are all the same. And yet we have a continuous function that's increasing the whole time. So how can you be continuously and strictly increasing and yet have the same y value at the beginning and the end, let alone in the middle? This is very perplexing. Now, the key to unlocking this is reading it very carefully. They said that on the open interval 0 to 1, f is continuous and increasing. We're increasing on an open interval. We are continuous on an open interval. So if we're increasing on an open interval, that means we're increasing between the endpoints. If we're continuous on the open interval, that means that the endpoints, although they might exist because they said our function's defined everywhere, we don't have to be continuous at the endpoints. So if you just use your imagination a little bit, a graph that fits all of these conditions might look as follows. So we have solid dots on the endpoints. That gives us our closed interval. We have solid dots or a solid line everywhere. This function is defined everywhere. And yet we have this little bit of a jump at the endpoints, which allows us to be continuously increasing and still hit all of these values at the beginning, the middle, and the end. So this is a crazy graph if you've never seen something like this before. Now, the important piece for this whole talk about min and max is that since we're not continuous at the endpoints, since we don't have continuity on a closed interval, which is the fine print here, that means our extreme value theorem does not apply. That means that we're not guaranteed to have a min or a max. Okay, so let's take a look at our answer choices. F attains both a min and max value on the closed interval. Well, it wasn't guaranteed, and here's certainly a graph where we don't hit a min or a max value. And then they're talking about a min but not a max but not a min. As it stands, the way this problem is set up, you're actually guaranteed not to have a min or a max. Because if you are increasing this whole time, then that means that you're going to be decreasing as you move to the left. So you can always go a little bit lower as you get closer and closer to x equals 0. You're increasing as you go to the right, but you never actually get to a point, so you can always go a little bit higher in this direction. So we're actually guaranteed we're not going to get a max or a min here, which gives us choice D.
For this problem, we're given the derivative of a function, f prime. It's this e to the negative x cosine of x squared stuff. And they want to know the minimum value of f of x on the interval from -1 to +1. Well, this is a graphing calculator question, or at least you're allowed to use one. So I think it would be good to check out f prime and see what it's doing. We know that the minimum is going to happen either at the endpoints or at a critical value. So let's at least see if we can figure out critical values for this thing. So to get this started, we're going to graph f prime on the interval from -1 to 1. So let me go to Desmos for that. So we've got, I'll just call this g of x, just because I can't name things with primes if I don't define f first. So we've got f prime is going to be e to the negative x, and then we've got cosine of x squared, and that's it. And that is a mess. Fortunately, we were only looking at -1 to 1. So let's go to our settings, and let me, for the x-axis, I'll make this like -1.1 to +1.1. That'll give me a good picture of what's happening. And here's the graph of all this. So let me just copy and paste that here. So we see that f prime is actually not crossing the x-axis anywhere. It's actually positive on this interval from -1 to 1. Well, what that means is that this thing is increasing across this whole interval. Now, if your function is increasing for an entire interval, that means that every step of the way it's a little bit more than it was before. So the most that they're actually asking for the min here, the least that this is ever going to be, the smallest value this is ever going to be, is when you started back here at the beginning of the interval, because you were increasing the whole time after that. So our min then is going to happen at x equals -1. Now, what is the actual minimum value? Well, it's going to be whatever you get when you plug -1 into the f function. We don't know what the f function actually is, so we're just going to call that f of -1, which matches answer choice A.